Okay, students, so let's go ahead and try this one on your own. It says calculate the molar solubility of calcium 2 fluoride if we had a solution that already had 0.25 molar calcium nitrate. So in this case, you can see that it's already calcium ions this time. So instead of there already being fluoride ions, we already have calcium ions that come from our calcium nitrate, which is a soluble salt. So I want you to try doing it the same way that you did the last one, right? Please pause this. Please actually try it on your own, and then come back and we can compare our answers. So hopefully you tried it, and now we can work on it together. So it said, calculate the molar solubility of calcium fluoride in a solution that already contained 0.25 molar calcium nitrate. So our first step is to think about our calcium fluoride. So our calcium fluoride is what we're looking at, right? We're trying to figure out what is the solubility of this calcium fluoride. So we have calcium fluoride. We know that it's going to break apart CaF2, right? 2 fluorides. Okay, so it's going to break apart into calcium 2 plus, which is obviously aqueous, and our 2 fluorines, which is also aqueous. We need to write our KSP expression. So our KSP is going to be equal to our concentration of calcium times our concentration of fluorine minus raised to the second power, right? Because we have 2 of them. Okay, now we can make our ice table. So let me just change my color for a second so we can see our difference. So our ice table initially, right, we don't need to worry about our calcium fluoride. That's a solid. Because it's a solid, it doesn't go in our ice table. So initially, what do we have? Well, if we look back at the problem, it said we had 0.250 molar calcium nitrate. So that means initially we have 0.25 molar calcium. Okay, so that goes in our ice table. We don't have any fluorine initially, right? Because it was calcium nitrate we had. So this is going to, our calcium will increase by S, and our fluorine will increase by 2S. So at equilibrium, we have 0.25 plus S. I know it's hard to tell the difference between my S's and my 5's. And then over here, we have 2S. We can then plug that into our KSP expression. So you do need to look up what the KSP of calcium fluoride is. If you look it up, you will see that it is 1.42 times 1.46. Sorry, let me erase that. 1.46 times 10 to the negative 10 equals, well, we can plug in our calcium, right? So we know our calcium is 0.25 plus S. And our fluoride is 2S, and that's going to be squared. We can make the S approximation here if you would like to. So I'm going to go ahead and get rid of this plus S. Because we know it's going to be extremely small. So what we can do now is let's go ahead and do some solving. So let's go ahead and square these numbers. So this equals, so this number, right, I'm just going to leave that there, equals, so we still have the 0.25. And this is going to be now 4S squared. Then I can multiply in the 0.25. Once again, we're still keeping that KSP number. Now we're technically going to have 1S squared. 1, obviously, right? We can divide each side by 1. We end up getting the same answer. So I'm just going to go ahead and erase that. Now we have s squared. So now we can take the square root of both sides. So I'm taking the square root of the 1.46 times 10 to the negative 10. So s now equals 1.21 times 10 to the negative 5th. Times 10 to the negative 5th. And this is molarity, right? This is large M. So our solubility of calcium 2 fluoride, if we already have a solution that has 0.25 molar calcium in it, the solubility now is 1.21 times 10 to the negative 5th molar. That is the highest concentration that will dissolve when we already have those calcium ions in there. We can double check on our PowerPoint, make sure that we got the right answer. I'm pretty sure that we did. Things are a little bit slow because everyone's on the internet, but there we go. 1.21 times 10 to the negative 5th. One other thing we can talk about is the pH. So if you think about pH, that can also affect our solubility. So if we have some insoluble hydroxide, obviously if it's a hydroxide, right, it's going to have a high pH. Therefore, it is going to lower the solubility of the ionic hydroxide. So we have some soluble ionic hydroxide that is able to dissolve in solution. What's going to happen is our insoluble ionic hydroxide would have a lower solubility. Also, if we have a very low pH, so the lower pH we go, the higher our solubility will be, because it will want to dissolve our hydroxide that has our high pH. We know that at a higher pH, we have an increased hydroxide concentration because that's our definition of high pHs, right? High pHs means that it's extremely basic, and so we have a higher pH. So we can still look at this expression, M times OH, right? This is some salt we know is going to break apart and give us our M, our metal, and our hydroxide solution. So it's the same expression, but in this case, we end up having a hydroxide, which relates to our pH. We can also have insoluble ionic compounds that contain anions of weak acids. So a weak acid, right, we know the pH is going to be a little bit low, right, because it's acidic. It is a weak acid, though, so that's okay. But if we decrease the pH, so we make it a very lower pH, we will have a higher solubility. So anytime that we have a weak acid, we know we'll get a conjugate base, right? So if we have a base, we lower the pH, we will increase the solubility. So that's the same for both of these problems here. Here is one that you can see we have a weak acid. Once we lower the pH, we will increase our solubility. So if we take a look at these, determine whether each compound is more soluble in an acidic solution or a neutral solution. So let's look at our first one, barium fluoride. So barium fluoride, if we think about it, barium, right, would come from barium hydroxide, which is a neutral solution. So we don't need to worry about that, right? That would be a neutral solution. Our fluoride, though, comes from HF. HF, we know, is a weak acid. So therefore, now we have this conjugate base. So therefore, it would be more soluble in an acid because we have a weak base than it would be in something that was neutral in solution. How about the second one? Silver iodide. Silver. What do we know about silver? Well, silver comes from, well, let's see, silver hydroxide. That's not right, is it? We actually don't even need to worry about the silver. Silver is not something that would come from an acid or a base. Silver would come from silver solid, so it's not something we need to worry about significantly. Our iodine, though, would come from HF. right? HF, hydroiodic acid, is one of our strong acids. So therefore, if it's a strong acid, the iodine now is not basic in nature. It is pH neutral. And therefore, it would want to dissolve in a neutral solution because now we have a neutral compound. Our second one, or our third one, calcium hydroxide. Calcium hydroxide is more soluble in an acid because our hydroxide ions are basic, and so they're going to want to dissolve in an acid. So we can look at the effect of our solubility on our pH. Go ahead and try this one. So we have iron 2 carbonate with lead 2 bromide. Which one is more soluble in an acid than in a base, and why? So please pause this and try. So hopefully you paused the video. Hopefully you came up with an answer. Let's see what our answer is. Well, they're saying that our iron 2 carbonate is more soluble in an acidic solution than our iron 2 bromide. Why? Well, our carbonate ions, we know, come from H2CO3. So therefore, this is a basic ion. So if we have some base, right, it would want to dissolve in an acid. Whereas if we look at bromine, bromine comes from a strong acid, HBr, and therefore would be pH neutral. So since we have something that's pH neutral with our bromine, with our HBr, that one would not dissolve in an acid solution, but our CO3 would. So our carbonate is a basic anion, and therefore we would end up being more soluble. Our iron 2 carbonate would be more soluble in an acidic solution. Please stay tuned for talking about precipitation.